Okay, thank you very much, Beatrice, for the introduction, and I'd like to thank the organizers, Scott, Nathaniel, and Jean-François, for the invitation. I was very happy to visit Cambridge on several occasions in the past years, and I learned a lot from this program. Okay, so in this talk, my plan is to define to you what this object is, and maybe the name seems fancy, but it's actually a simple object. And everything I will be talking about is joint work with Thierry Lévy from Paris. So the goal of the talk is to define a generalization of a uniform spanning tree, which is somehow parameterized by connections on a graph. So it's lucky that we had the course last week by Shurav. So you remember that we had the situation where we had a graph, and on top of each edge we had each directed edge we had some matrix. He wrote it U for, because I'm used to writing it H, but so matrix which which was sitting like if you look at the reverse edge, you get the inverse, and this is something in a unitary group for some n integer n. And so one situation where this this sort of picture comes is so what Schwab was talking about, so namely lattice gauge theory. And if you want to think of a very concrete situation where you could have such data, such linear data on a graph, think maybe of a graph which is not embedded just on the plane, but maybe embedded in some manifold. And at each vertex you can look at the tangent space on this manifold. So this is a bunch of vector spaces, and then the edges drawn on the surface define for you parallel transport connecting these different vector spaces. And okay, in certain situations you can just represent this by an operator, and here I've done an identification so that we just think of matrices. So the idea is, can we define some classical statistical physics model like the uniform spanning tree, but which take into account this additional linear data on the graph? So this is kind of sort of a discrete geometry maybe problem. And okay, the goal of the talk is to explain how to make sense of this. Maybe I can point out that in a previous paper or work with Thierry, we addressed a slightly simpler question, at least for us it was simpler, which was to look at, you have on graphs you have natural objects which are the discrete Gaussian free field or random walk and loop soups and local times of these, and you have isomorphisms between them, and we've heard about them in some of the talks before. And it's possible to define a generalization of discrete Gaussian free field. Would now take vector values, and of loop soup, which are now weighted by these Wilson loop expectations, as we saw, and to define corresponding isomorphism. So that was one step in our kind of project to consider this type of processes. But today I will focus on the case of trees, and so I'll start by recalling, how one can view the uniform spanning tree on a graph, and I'll focus on specific properties which are relevant for our generalization. So you all know what a spanning tree of a finite graph is, just a subgraph which has no cycles. And so let me just draw one for concreteness, like this. And okay, they have a long history. I will be brief by lack of time. Actually, I will just introduce a notation. So let's say G is our graph with vertex set V and edge set E. And I will think of E as being oriented edges. So both orientation of each edge are in this set. When I think of an edge as being unoriented, I'll write the set of these as this. And maybe if I need, because I will need it for convenience, to choose just one orientation for each edge, I will write a subset of E as E plus. That's the choice of direction for each edge. Just convenient to pick a basis, as we'll see in a second. Okay, so as I said, there's a long history, and maybe one of the first place where this appears is in the study of electrical networks by Kirchhoff and others. And there in some sense, that's where the uniform measure on spanning trees appeared for the first time. So the problem was, imagine you put some current entering this okay, so you view your graph as a network with each edge representing a resistor of unit resistance, and then you impose some current going inside, say, this vertex, and going out from this vertex. And then you ask, you pick some edge, and you ask what is the current flowing through that edge. So the answer that we can write in terms of spanning trees is that the intensity induced in E is the probability that in a uniform spanning tree, the unique path going from X to Y, so you look at the event that the unique path going from X to Y in T, takes the edge E in that direction, minus the probability that the other event occurs okay. So that's one place where it occurred, and then it had some later developments. Another important place, which I won't mention much, but is actually in the background of everything, is combinatorics, and in particular the theory of matroids. And spanning trees there were a motivation for Whitney to introduce this notion in the general framework, and there was an example of basis of matroid. And later on, of course, this was famously used, or further developed by Todd and his famous Todd polynomial, which, as you know, is related to FK model and all these spanning tree expansions of this polynomial. I won't talk about this. And of course, as many people in this audience know and are more experts than me on this was taken up in probability, and so there were many people, I won't write all the names, but Burton, Pimentel, Lyons, Perez, Benjamini, Schramm, and many people in this room as well who studied a uniform spanning tree, in particular infinite volume limits on ZD and other graphs and groups, and in 2D scaling limits and relation to SLE, etc. And of course a relation to other statistical physics model as sand piles and FK model, etc. Okay, so all of this is very nice, and I will say something. I will start, at a much more basic level. So, what is the property that I wish to stress about spanning trees? Is the fact that it's a determinable point process. So, this is a notion which, is actually very old, because determinable point processes were observed first in eigenvalues of random matrices by people in the earlier 20th century, but in the framework I'm using, this is a definition which was proposed by Odile Mackie, 1975, and the theorem, which is due to Burton and Pimentel in 93, is that the UST uniform spanning tree is a determinable point process on the set of edges, I have a name for this, on E. Okay, so what does this mean? This means that there exists a matrix K, which is, indexed by, actually I will take this set, so this is convenient to have chosen an orientation, EI, EJ in E plus, such that the probability that you see a collection of K edges that you fix yourself in a uniform spanning tree is the minor of the matrix K corresponding to columns and lines indexed by these things, these indices. Okay, so I should tell you what is the matrix K now. Okay, so I will be brief in introducing notation, but I just need a few. So basic definitions. So when you have your graph, I'm going to denote by omega 0 just the functions, the real functions on vertices, which is just, you can think of as r to the v, and then omega 1, which we think of as the real one forms, which are antisymmetric functions on edges. So functions from e to r, such that omega of minus e is minus omega of e, and this is naturally isomorphic to r to the e plus. Okay, and there's an important map, which is a kind of discrete derivative going from omega 0 to omega 1, which to a function associates df of e, which is the difference at the two endpoints of the edge. So if you have edge e here, going from e minus 1 to e plus, you just take the difference. Okay, and so there are scalar products on these two spaces, which I won't write down, but okay, just to think of, canonical Euclidean structure coming from these two Euclidean spaces. So there's an adjoint D star to this map, and we have this easy identity, which is that omega 1 is a direct orthogonal sum of these two spaces. Okay, I'm almost there. Now, what I claim is that K is just the matrix of the orthogonal projection on this space in a web-Trojan basis. And what is this basis? So there's, I will call it B. So for each edge in E plus, I consider omega E to be the one form which has support just on E. So it gives an edge plus 1 if this edge coincides with E, and minus 1 if that's the opposite edge. That's omega E. That's a one form, just indexed with support on E. And so these omega E's form an orthonormal basis of omega 1. And K is actually the matrix in the matrix B of what I will write P sub image of D, which is the orthogonal projection on that space image of D. Okay, so that's one way of thinking about what the uniform spanning tree is. It's, at least on a finite graph, it's, you see if I write here a little bit? No. It's a determinant point process on the set of unoriented edges with a kernel given by this matrix, which is just the matrix of this projection in this particular basis. Now, I want to come back to our, this initial question. So, and I will write maybe some definitions on this board so that they stay. We could say, okay, if we want now to define something which is like a uniform spanning tree in this enhanced setup, we will just mimic everything, okay? So what is our setup? Remember that we are thinking that over, so I would just make a zoom of how our graph looks like. So now you have not just a real line over your graph, but you have a bunch of vectors which are glued together by the data given by this connection on the graph. So if I zoom in locally, the picture you should think of is as like this. So you have a vertex X, an edge E, and a vertex Y. I just give them names because even if we identified all of them, it's just more convenient. So all of these vector spaces are isomorphic, and this one is actually equal. It doesn't matter on the orientation, and they're all copies. Let's say I'll just take the complex numbers for 2c to some power n, and therefore these matrices, which we think of in UN, they are just maps connecting these fibers. So there's one, for example, this is going from X to E. I will denote it H X E, and there's one here going from E to Y. I will denote it like this. And they're all unitary with respect to scalar products in these fibers. Okay. E is an edge. It's this edge. So you will see in a second why I need this, because I want to construct these two spaces. So I have also omega 0. Now it's the sections of this bundle. So like vectors sitting on vertices. So this I can identify it if you want with the direct sum of these fibers. And omega 1 I take to be the one form but with values in Fe. So this is like the omega E inside Fe, collection of those such that omega of minus E is minus omega of E. And this is isomorphic to the sum over E in E plus of the Fe. And you see I need actually to introduce this intermediate space because I want to now introduce a map D which is like there, but which now depends on this choice of H. I hope you still can see.
You just have one matrix for an edge, and here you have a matrix going from X to E.
Yes, that was to simplify the picture here. But if I want to introduce this structure, I need actually to split it in two. But you could make a choice. I mean, you could say it's just kind of a square root of this thing, and or you put identity on one. I don't know. But I need for this construction to have it split like that. And therefore, I have a map which is very similar to the previous one, except that now you do what you think you would do, which is that you map this here, and take the difference. So you have, in my notation, what it is. Okay, and I hope you still can see. And of course, now we have also exactly the right same splitting, which is, now this depends on H, everything. Okay, so you can say, well, this is exactly the same story. So if I want to define a point process which resembles spanning tree somehow, I just take a determinant point process which is associated to the orthogonal projection on this guy in a certain basis. But actually, what is the reason of all this thing is that is the question in a certain basis. So, so let me talk just about gauge transformations for a second. So you see that when you have chosen these, I mean, you have these vectors now sitting over edges, and there's not actually a preferred choice of basis of these vector spaces. And in particular, you will see there's a group which acts naturally on our situation, which is, you know, take the product of unitary groups. So you know, for at each vertex, I can perform a unitary transformation. Here, I can perform a unitary transformation. That's called a gauge transformation. Basically, it corresponds exactly to changing a basis. Okay, and J, so an element, let me call this group G. This is like our gauge group. So if you have an element J in G, it acts on a connection in the following sense that J of H on the segment EX is just going to be JE H EX H inverse. Okay, that's a natural kind of conjugation thing. And you see now that if you perform, and okay, and I think probably Schwab mentioned the gauge invariance at some point in his lectures, and it's an important concept you want to have. I mean, sometimes it's important to you know, single out the quantities which are gauge invariant because they correspond to the measurable, physical measurable things. You see now that this decomposition, if you perform such a gauge transformation, it will actually move a little bit. So why? Because D of JH is like J acting on the edges, composed with DH, composed with J minus acting on vertices. So this image of DH, GJH, I'm sorry, is rotated somehow by this J if you apply a gauge transformation. And okay, our motivation is that we would like to have, okay, if I view a determinantal point process as associating to a subspace a certain point process indexed by a basis, then I would like that if I perform such a transformation on the first object, then it also transforms somehow my random variable. But okay, how am I going to let unitary group act on a point process? So that's why we are led to thinking that maybe the right object is actually a random subspace. So instead of thinking of your random variables as being edges on your graph which are there or not there, you will have actually over each edge some random subspace sitting in the fiber, and all of them are correlated. So it's kind of a field of random subspaces. Okay, so that's the main idea. And before going on, I will just say first how I view, maybe I can say it here, the uniform spanning tree as a random subspace, and then you will start to see how this is going to work. Well, if I have a tree T, I can associate to it a space which is the sum over all edges in the tree of well, I'm back to R anyways, of the line generated by this omega E, the one form just, okay. And this is a subspace of omega 1, right? I just basically take over the tree, I claim you just take the subspace it generates, so subspace of omega 1. And now you will see some interesting features when you start to think like this. So claim one is that actually we have the following decomposition. So omega 1 is equal to qt direct sum, which is not orthogonal, but I don't have a different sign, so okay, to this cycle space. So you see, actually you can view a tree as a supplement to the cycle space, as a subspace. And moreover, if you start to look at the expectation, so you look at you look at the projection on this space parallel to this space, it's a non-orthogonal projection. If you take the average, it is actually the orthogonal projection we are interested in, the projection on MT. So if I take the projection on Qt parallel to the cycle space, I get back the projection on MT. So I don't know how I'm doing on time, but already at this time maybe I can pause to just make a little take-home message that one way you can think of as the spanning tree measure, it's trying to make a random approximation of the space image of V using the a priori information that you are only allowed to use the building blocks of these edge bases. And moreover, you do it in such a way that it's reasonable in the sense that if you take the expectation of this random space, it's actually the space you're looking for. Okay. So I think now we're ready, and I'm ready to introduce to you the general type of measures we construct. So if you were not interested about the spanning tree motivation, this is completely independent now for 10 minutes, which I hope I still have. So the idea is that we will give a recipe, define a family of measures on subspaces of some space. And I claim that determinantal point processes are just a particular case when they are living actually on a very small part of subspaces which are given by bases. So I just need to introduce a few definitions, which I will try to do as quickly as possible. So, okay, for now on, I'm just thinking I'm on the base field of the complex numbers. And if you have some vector space of dimension d, for all n less than d, I will denote by grn of e to be the variety of all linear subspaces of dimension n in E. So n-dimensional subspaces of E. So this is a very nice space. And yes, maybe also I denote the full Grassmannian to be the union of all these things. So we just pick we're just considering, all the subspaces, all the linear subspaces of some vector space. This will be our kind of our probability space. And if you have an inner product on E, then the unitary group of E acts on this thing, on all of these spaces, and there's a unique invariant measure that you can put on this up to a scale, and so I will denote by nu NE is the unique invariant measure on GRN of E with total mass D choose N. So the thing is that you can think of this as being kind of a continuous counting measure. Instead of just picking, subsets of size n in a d-dimensional, size d set, you're picking linear subspaces of dimension n in a subspace of dimension d. So that's the natural way to put on this. And okay, so the very important thing now is that somehow the randomness we are going to define comes from the fact that your space comes with a natural splitting. So splitting for me is just a decomposition of the space in a direct sum, orthogonal sum of subspaces. So maybe just to, because we had these examples before, for example, in our case, this omega 1 comes with a natural splitting, which is that it is written as a direct sum of these fibers of edges. And they are not necessarily just lines. They can have some dimension, and they can have also not the same dimension. Okay, and now the measure we will study is supported on a certain subspace of the Grassmannian, which depends on the splitting. Okay, I will call this a splitting and denote it sigma. Sorry for the many notations. And so what is this? It's like before. It's all the subspaces of E that you can build from building blocks inside this EI. And a very intrinsic way of writing this is just it's all the subspaces of E. So just basically Q is equal to the sum of its intersection with all the QIs, all the EIs. So basically it's like I'm picking some subset here, some subspace in E1, E2, etc. I'm just taking direct sum. Okay, that's going to be my. So the coarser you see that if the splitting is just as a. Okay. Should write this out. If your splitting is just a splitting in lines, actually what you're doing in disguise is just counting on a finite set, and that's exactly the whole point. The whole thing. So if all the EIs have dimension 1, then I claim that this GR for all I, then is GR of E sigma. It's just all the subset of S. If S is the set 1 to S, because I'm just picking. I can just create a subspace by picking some subset of the basis. So it's really like picking a subset of the set S, which is what is. And okay, so on this space GR E sigma, there's a natural measure, which also I won't define in great detail. So the unique invariant measure with total mass 2 to the D, and which really mimics the counting measure. I don't describe it in great detail, and which reduces to the counting measure in this example. And okay. So now I'm close to define to you what is this measure, and to give you a theorem that they exist and that they are nice. For this, I just need to introduce one more ingredient, which is the notion of incidence measure. So you see from all of this that basically we are trying to replace the usual combinatorics of a set and its subset. It's like a partially ordered set, by now taking a space and all the subspaces inside it, which is also a poset. And so there's also all these things of Möbius inversion, inclusion exclusion formula, except they are now more continuous than combinatorial. So if I have a measure mu on this space GRE sigma, I'm going to define its incidence measure Z mu to be basically an average under the measure mu of this kind of continuous counting measure on all the subspaces of Q. So you should think that in the case where this is only just a set, this Z mu is really in the simple case, Z mu is just becoming a sum over all subset I of S, mu of I, and then I'm summing over all subset J, it's a counting measure, J of I, the Dirac mass at J. So in particular, if I compute Z mu of some finite subset J, say mu is a probability measure, then you see that this is actually the mu measure that J is included in I, where I is distributed according to mu. So you recognize maybe that this is exactly what we had somewhere when we wrote determinant processes as saying, okay, what's the probability that some fixed subset is inside my random subset? So you see that this is the natural notion, extending it. So now there's we are led to the following definition that a measure on a measure on subspaces is called a determinantal, so mu probability measure on GRE sigma is a determinantal subspace measure with kernel K, where K is some linear isomorphism of E, if its incidence measure Z mu is absolutely continuous with respect to this counting measure, and the Radon-Nikodym derivative is given by a determinant in the following form. So for all Q, this thing is equal to the determinant of this map, and KQQ is the compression of our operator K on Q, meaning that going from Q, you embed it in E, then you use the map K to map E into E, and then you project back onto Q. So in the matrix language, when you're just dealing with bases, etc., this would correspond to a principal minor of your basis. Okay, so that's the definition. And the main theorem is that it exists. How much time do I have?
Maybe 10 minutes?
Okay. It's going to be intense. Okay, so main theorem, just so if K, so if you have E sigma, an inner product space with splitting, and if K is a self-dual operator which is bounded between 0 and the identity, then there exists a unique determinantal subspace measure on GRE sigma with kernel K, which will denote mu K E sigma. Okay, so in the remaining time, let me just try to give you an idea of what this thing is. So first of all, because we don't have time, let's just focus on the case where K is, and actually it's a fundamental example, K is an orthogonal projection on some subspace H as before. So just assume now from now on that K is an orthogonal projection on some subspace H. Then how can you view this? This is exactly like in the story I told you at the beginning. Well, first of all, so H is a random subspace which is built from these building blocks EI, and almost surely it's a supplement. No, it's called. Let me call Q this random variable under. So Q is distributed according to mu h and sigma. So then almost surely this is actually a supplement to the orthogonal of h. So you're still, doing this story as I told you before, and you have this the fact that it's kind of an unbiased estimator, like probability. I mean the projection on Q parallel to h orthogonal. If you average it over this measure, this is just the orthogonal projection on h. And I think it's important that I try, even though I don't have much time, to just explain one more thing, which I hope is not too technical, but which actually gives meaning maybe to what is this family of measures. I mean, how they behave together. So first of all, is there maybe is it relatively clear what the statement is? There's some measure that exists. So okay, let me just try in a few words to tell you one property which I hope enlightens a little bit what this is about. But it involves just a little bit of algebra. So one way to, I mean, that's how at least physicists, I guess, view this thing, is that determinant point processes, they are random variables describing the statistics of fermions. What does this mean? Actually quite simple to describe, I mean in a certain way at least. So this is a crash course in 1 minute of recall what is exterior algebra. I hope many of you know it already. So you can look at the exterior power of your space E. Okay, if you want to think about it concretely, just think that lambda n of E is like a subspace of the nth tensor power of E, so just words in n vectors of E, to which I applied a kind of anti-symmetrizing map. So to some tensor, I define this thing. It would look like the determinant. We just average over all the possible orderings of your vectors. Anyways, when you do it like that, then you can define a product on this algebra by saying I take two guys, and the wedge product is just the anti-symmetrization of x tensor y. Okay. Now, why is this useful for us? Because there's this very famous way of viewing a subspace of E as an element of lambda E. So if I have H, a subspace of dimension n of E, I can look at all the E1 wedge En where EI is the basis of H, and this is a line inside lambda n of E. So there's also a scalar product actually on lambda n, and this is very reminiscent of the determinant story, because the scalar product of two such vectors is just the determinant of the Gram matrix of scalar products EI Fj. And that's how, for example, Russell-Lyons describes the determinant point processes. So once you have the scalar product, I can informally pick, if I have some H, I will associate to it some state psi H of norm 1 inside lambda n of E. And you can think of this as being the state. You have n fermions. Each of them has a state space E. So they live in this, that's the definition of a fermion basically. They live in the tensor power, but they have to have this intersymmetry property. And I pick one which have this kind of wave function which is normalized to be 1. And now, the nice thing is that if you have a splitting of E, like we have, it induces a splitting of the nth exterior power of E. So when E is split like that, lambda n of E has an induced splitting over all multi-indices when basically looking at this guy. And this is a multi-index, so n bar means n1 and s, and they all sum up to n. So now you recall Pythagoras' theorem, which is always good to remember, and you write that 1 is the norm of ch, is basically the squared norm of the, this ch decomposes in this basis, so I will write it like ch of n bar norm squared. So I see that from this defines a probability measure on the n bars, right? I mean, this is just positive numbers. Basically, that's how determinants on point processes are defined. And what I claim is that what is the relation with our thing is that this psi h of n bar squared, this is exactly so I have this probability measure, remember there, mu h of E sigma. I can ask, okay, what's the probability that my space, random space Q, has dimension n1 in E1, n2 in E2, ns in ES. So Q such that the dimension of Q intersected with EI is equal to Ni. And I claim that this is an equality. So somehow, if I can phrase a bit loosely what we're doing is that we construct a family of measures on subspaces of a certain space E, which is given by two things. First of all, a subspace H, and then a splitting of your space, and the randomness comes from how these two sets of spaces are with respect to one another, in what position they are. And somehow there's this nice property that we try to respect this Pythagorean proportion. So we always have the fact that, whatever the splitting, you always have that the probability that this random space you constructed has this and that dimension in this splitting is exactly this wave function evaluated at n bar. So how much time do I have now? Okay. Okay, so now we'll come back to the first story, and just take this as a black box if you want. So now we're back to this setup, and we just defined, okay, what is a quantum spanning forest? At least I will tell you what this is for us. Well, it's just the determinant of spanning. So QSF is the, sorry for the acronym, is the determinant of subspace measure on omega 1, given by this splitting in fibers, and associated to the orthogonal projection on the image of DH. Okay, so now in the remaining few minutes, can I tell you just a few things about why maybe you should care what this thing is. So first of all, of course, in the case of a trivial rank bundle, this is just the uniform spanning tree. When n is 1 and h is trivial. Then when you still are in n is 1, but you start to have a connection maybe in u1, which is non-trivial, then you see appearing these things which are called cycle-rooted spanning forests, which were first introduced by Foreman, but in a non-probabilistic setup, and then by Kenyon in 2009. And now, so you increase the dimension n, and intuitively what you have, I don't have time to explain it, it's a bit like if you had n spanning tree-like things or forest-like stuff, except that you can't really distinguish them, so they are superposed and they generate this random subspace. So kind of n-CRSF which are intricated in a loose sense. Maybe just another remark is that you can define this naturally on infinite graphs. So for example, just on ZD, and there's a similar notion of wired and free measure and one dominates the other in the sense that it's the subspace is included in the other subspace. Yes. So maybe okay. There's also some relation, because when you do actually choose a basis, which you're allowed to do, nobody said you can't, then you're back to kind of a determinant of point process, and there's, I'd be happy to talk with people, because maybe, I mean, it's a kind of a percolation type model with negative correlation, except it's close to a tree, so I don't know if it would be interesting to know if this can be related to near-critical spanning trees or other FK for small q. So maybe just to conclude, I will just okay, make one statement to just relate a little bit to other to random walks and stuff like that. So remember this little electricity problem from Kirchhoff. So now you can actually define something equivalent in our setup, and there is an analog of the effective resistance, which gives you the. So now your graph has some holonomy, but still you can say, okay, I plug in some intensity vector, whatever that means. It's some vector here, and then I'm asking what is the current induced here. So basically, you want to find some current. So a current has to be in the image of V. It's something which is the difference of a potential, such that V star of I is equal to V star of eta. And unsurprisingly, this has to do with the orthogonal projection on this space. And actually, you can write I of V as in Kirchhoff's case as okay, maybe it's not completely apparent, it's the same thing, but the projection on our QSF QE on the edge E parallel to this cycle space applied to eta. So this is somehow an equivalent of the effective resistance, which is now an operator, but which still has nice properties such as the Rayleigh monotonicity property. And maybe just okay, just to finish on something slightly different to connect a bit more to random walk type objects. So there's a generalization of this problem where basically you imagine that you plug in something at some point A, and you plug out some current at some point Z. And you know that in the theory of random walk and electrical networks, the effective resistance between these 2 points has something to do with the escape probability that random walk going from there touches Z before it comes back to A. And actually here there's a similar statement which is just slightly different, which is that, so if you, I don't define it, but okay, there's an effective conductance which is the inverse of this resistance, and essentially it's equal to something which is not really the expected, the probability of escape of a random walk, but rather its expected holonomy of escape. So what I mean by that, maybe you remember from the course last week that the holonomy of a trajectory in such a gauge field thing is just multiplying matrices along the path. So if you take a random walk started at A and you look at it until it hits Z, this defines for your trajectory, you can compose matrices, this defines the holonomy. Actually I want to do it in reverse, so I put -1. And I look at this on the event that the random walk escapes. So it touches Z before it comes back to A. Well, essentially, as in the random walk case, this is this effective conductance, except that you have to compose this with an operator of harmonic extension from Z to A. So this, okay. So I haven't explored more this direction, but you see that maybe you can try to look at statements such as recurrence transience, except that now it's a bit different because it's just you have this thing which may be 0, although this probability is not 0. It's a different, slightly different thing. I should finish. Okay. Well, yeah. Okay. Okay. Just 1 minute, maybe. So, well. Okay.
Go ahead, take your minute.
Okay, I'll just take my minute. No, so maybe because some of you are familiar with Laplacian determinant, and we've heard about this before, and you know that spanning trees are related to this. Counting spanning trees is related to determinant of Laplacian. I just want to say, and because maybe this also relates to other questions that we might want to discuss with some people, if you define the Laplacian to be just this operator d star composed with c, then actually a sort of equivalent way of rephrasing this is that there's a way to write the determinant. Not usual cases would be a sum over spanning trees of coefficient 1, and now it's actually a sum over these subspaces of a certain weight against the counting measure. And okay, I won't write this way down, but it's relatively explicit, and in particular we know combinatorially what is the support, so what is the analog of this spanning tree-like structure, and what is the weight in this. Okay, this explains that it might, we'd like to further understand maybe relations to other objects which are encoded by this, such as this Gaussian free field and loop soups and things like that. Okay, I'll stop there. Thank you.
Other questions? So what is this weight?
It's not that explicit. I can show it to you later. Like it has an I mean, the best expression I actually know involves another determinant, but of a small thing. But it's still not like in the case of spanning trees, it's just one this coefficient. So that's okay. It cannot be that easy, but.
When you started on your setup on the left, I thought, there's a nice way to think of it with perfect matchings type thinking. And then it started splitting, and so is there some way to represent
so
to have some
yes, so I guess
line of
so I guess if your graph is planar, it's not planar, I don't know. If it's planar, I mean, it's possible, probably it's even written in a paper of Julien maybe, it's possible to write an operator k, which going from, it's like,
but then for your
and which is kind of a square root of the Laplacian, and but so in the particular case, because in the particular case when you're just in SU2 or U1, maybe there's an interpretation in terms of double dimers and stuff, and I'm not aware of something you can do when you're in higher rank, and maybe for the moment it's a good question. I don't know actually, because now we're just focused on the spanning tree case, so I'm not sure that
Let's thank Adrien avant de speak, because